Okay, in this video session we will see what is the heat transfer through the fins. Okay, fins are used to increase the rate of heat transfer through its body to the surrounding. So there is convection heat transfer will be there. So let us see what is the finite element formulation of the fins. The purpose of the fins is to increase the rate of heat transfer or to give the or to remove the heat from the body where there is excess heat is involved. Okay, let us consider a fin element. You can see how the fins are. It is the additional things to the engine. Okay, it is a fin element where the heat is required to be removed from the body to the surroundings. So from the body to the surroundings, so it is a convection heat transfer. Okay, the whole fin is considered as one element. So the temperatures are T1 and T2 at node 1 and 2. You already know how to do the shape functions, how to find the shape functions for the linear element. Okay, for interpolation functions are used here. T equal to a0 plus a1x. At x is equal to x1, t is t1, and x is equal to x2, t is equal to t2. Okay, then you need to find a0 and a1. After finding a0 and a1, again you substitute in this equation. Okay, then you find what are the coefficients of t1 and t2. Okay, those are shape functions n1 and n2. Okay, we have done it for many times for many types of elements. So the shape functions are x2 minus x by le, n2 is x minus x1 by le. These are the shape functions. And similarly, the element strain displacement matrix, it is also derived many elements. It is 1 by le minus 1 1. Element conductivity matrix, we know the element conductivity matrix k is equal to ak by le 1 minus 1 minus 1 1. Okay, how the conductivity matrix is derived? Okay, again it is the same method. It is done by the strain energy. Okay, in the strain energy, the displacement or the nodal displacement terms are removed. It will be element conductivity matrix. Okay, what is B here? 1 by le minus 1 1. It is the transpose and it is the material constant. Okay, for conduction you need to take k value. Okay, it is already done in the previous video sessions. Okay, so by this simplifying this, you will get k is equal to ak by le 1 minus 1 minus 1 1. Okay, it is the element conductivity matrix where a is the area of the element, k is conductivity, l is the length of the element. Similarly, we also derived convection matrix. How to do the convection matrix? Again you need to consider the strain energy. Okay, convection, it is depends upon this area, surface area. Already we know the shape functions, and here the material property is convection property, that is heat transfer coefficient. Okay, what is the area here? The surface area, that is can be defined as p into dx. Okay, for a rectangular element it is 2 times of width and 2 times of thickness. Simplifying this and integrating, we have hple by 6 2112. Okay, it is derived in the previous videos. You just go through that videos, where p is the parameter, l is the length of the element, h is the material property, that is convection heat transfer coefficient. Okay, similarly for a different condition you will get the equations. It is for the fins. Okay, fins are used for the to remove the heat from the body, to remove the excessive heat from the body. Okay, let us solve some of the problems on the fins. Okay, let's start the first problem. Okay, here we have one pin where one end it is specified with some temperature. It is shown as fixed. Okay, if it is fixed means it is specified temperature. At this specified temperature at this node there will be no heat transfer. Okay, it is specified temperature. And this is a fin. It is of 5 centimeter length, and the area it is 1 centimeter radius. So you convert it to area, pi by 4 d square. You consider d as in meters. And the temperature, outside temperature or the environment temperature, it is 40 degrees Celsius, and at node 1 it is 140 degrees Celsius. Okay, the element in this problem it is formulated as 2 elements. So 2.5 centimeter, 2.5 centimeter, 2 elements. So for the 2 elements we have 3 nodes, node 1, node 2, node 3. Now as this is a material, as this is a fin, it is an element, definitely there will be heat transfer in the material. So you need to find the conduction matrix. Also, as it is a fin, there is heat transfer to the outside environment through the node 2 and node 3. So you need to find the convection matrix also. Then you add these conduction matrix and convection matrix together. Okay, that is the global conductivity and conduction matrix. Okay, then by using the equilibrium equation you find the unknown nodal temperatures. That is in the similar fashion what we have done in bars, beams and trusses. Okay, let us find the conduction matrix. First you take discretization. So the body or the element, this body is divided as 2 elements. Element 1 which has node 1 and 2, element 2 which has node 2 and 3. So the temperature at node 1 it is 140 degrees Celsius, and T2 and T3 which are unknown. Okay, the given material properties are convection heat transfer coefficient 5 watt per centimeter square Kelvin, and thermal conductivity 70 watt per centimeter Kelvin. Okay, you have to take care of the units. It should be same or it should be compatible with the other temperature. For example, if it is in degree Celsius, in the material properties also you should consider degree Celsius. Better you convert this temperature in Kelvin. As we have the material properties in Kelvin, see here, watt per centimeter square Kelvin, you convert it to Kelvins by adding 273 degrees Celsius. Okay, let us find the conduction matrix. For the element 1 we have already the equations AK by L, 1 minus 1 minus 1 1. Okay, by this you find the area is, it is constant for both the elements, so you consider area same, and thermal conductivity it is also same, and lengths are also same, so you will get the same values. But you find the global stiffness matrix considering the corresponding nodes. Then you consider the convection matrix. We already derived it for the HPL by 6 2 1 1 2. Okay, how to find the perimeter? Okay, we know the radius, so by using pi d or 2 pi r you can calculate perimeter. So HPL by 6, H is 5, P is perimeter, and L is 2.5 centimeter for each element. Here also you will get the same terms in both the matrix, as we have the same H value and same perimeter, same length. Then you find the global matrix. You know how to find the global matrix. Okay, you consider the corresponding nodes 1 2 1 2, and here for the element 2 it is 2 3 2 3. Then you add conduction matrix and convection matrix. Okay, the corresponding values are get added, so it is the global stiffness matrix or global stiffness matrix. Okay, now the main reason for the fins force vector. Okay, while finding the nodal temperatures you have to use the equilibrium equation K Q is equal to F, where K is the stiffness matrix, Q is the nodal temperatures, and F is the force vector due to convection. For the convection force vectors, okay, you are using this expression to find the force vectors H T infinity P L by 2, where H is the convection heat transfer coefficient, T infinity is the outside environment temperature, P is the parameter, L is the length of the element.